In our last video, we described in general what buffers are, right? A buffer is a solution that has a weak acid and its conjugate base present. We also learned how buffers work to resist pH changes. These buffering components act as soldiers and react against strong acids and strong bases, converting them to weaker versions. Now, since buffers are so important in the body and in the laboratory, we need to be able to do some math with them, right? And the math is not going to be as straightforward as the pH problems that we did with strong acids and strong bases. We need to be able to calculate the pH of a buffered solution, and therefore we're going to have to think about what's the concentration of H plus in these solutions. Now, the reason why it's not so straightforward is when we were dealing with strong acids, it's because a weak acid only very rarely will dissociate to form H plus. So if we know the concentration of our weak acid, we can't just say that that H plus is at that same concentration. It's at a much lower concentration, and it takes a little bit of work to figure out what that is going to be. Now, how do we know how often weak acids are going to dissociate to form H plus? Well, we know that each weak acid has a Ka associated with it, and that equilibrium constant really defines how often that H plus dissociates. Now, what's the Ka for this general weak acid? Well, like any big K value, it's equal to the concentration of the products, in this case H plus times A minus, over the concentration of the reactants. Okay. This is how we're going to start to build an equation which is going to allow us to calculate the pH of a buffered solution. pH is the negative log of H plus. Now we have an equation with the concentration of H plus in it. So really all our job is going to be here is to try to get pH to one side of this equation and everything else to the other side. So let's start working on that right now, right? Now, if we're going to want pH, then we're going to take the negative log of our H plus. So let's go ahead and take the negative log of both sides of this equation. So we'll say negative log of Ka, right, equals the negative log of all this stuff, right? H plus, A minus, over HA. Now we know negative log is another way of saying P of something. So this is going to be the pK over here. Now, mathematically, when you take the negative log of a ratio like this, what we can do is say that this is equal to the negative log of H plus, and we can separate it from the rest of this ratio and minus the log of A minus over HA. Okay, now that we've separated this out, it's going to be pretty easy to just isolate negative log of H plus, or pH, onto one side of the equation. Let's bring this over to the left side and call it pH, right, instead. So what is pH equal to? pH is equal to the pKa plus, right, we have to get this to the other side of the equation. So we're going to turn that into a plus instead of minus, the log of base, conjugate base, over weak acid. This equation here is a famous equation that you are going to have to memorize. This is the Henderson-Hasselbalch equation. And if you've taken organic chemistry, you've used this before, and now you probably have a better idea of where it comes from. Really, the Henderson-Hasselbalch equation is a super useful equation that can be used to calculate the pH of a buffered solution if you know the Ka of the weak acid, the concentration of the conjugate base, and the concentration of the weak acid in the solution. You can solve for pH. And now you know where it came from. Really, it just came from a rearrangement of this Ka expression and getting pH on one side to derive this. Now, this equation is super useful, right? We're going to show some examples of how you can calculate the pH of a particular buffered solution. And we're also going to show some examples of how the pH of that buffered solution changes if you insult it with an acid or a base.